All right, so let me give you one more example of things that we need to think about if we're going to change our computing teaching practices to really reach CS for all, computational literacy for all. So students are often overwhelmed when programming. We have this wonderful quote from Mike Clancy and Marshall Lynn from the 1990s, where a student says, "You've taught me so many details, I don't know which ones to use when." So how do we convey to students what the purpose for the different parts of the program are? Richard Catronbone, a colleague of mine at Georgia Tech, invented a way to label the subgoals in the examples provided to students. He did this work, and it's been done in statistics, it's been done in chemistry, but nobody's really tried before to say the subgoal labeling that works really well in these other subjects. How well does it work in computer science? Can we use subgoal labeling to help students understand better how programs work, why the parts are there, to help them to be able to transfer their knowledge of programming? So Lauren Marjolou was a PhD student working with Richard and me, and she did the first experiment trying out subgoal labeling for computer science. So here's two lists of how to use something called Android App Inventor. It's a drag and drop block-based programming environment for building Android apps. On the right-hand side is the list of steps that we want to lead students through in building a particular program. On the left are the same steps, but we're going to identify the subgoals. So the first thing you're going to do here is define the variables from the built-in. Here's 5 steps. And then you're going to handle events from my blocks. Here's a couple more steps. So this is an example of how we insert subgoals into a list of steps. I'm going to bet that everybody would recognize this as a pretty traditional screencast. If you're going to describe to somebody how to use a piece of software, you might produce something that looks just like this. Barbara Erickson made these videos to help teachers learn how to use Android App Inventor. Lauren Marjolou took these and inserted into them her subgoal labels. So this is what the subgoal labeled video looks like. Okay, I'm hoping that you're going to look at this list of steps and these videos and say, that's a pretty minor change. We inserted some subgoal headings and we put some call-out boxes into the video. Okay, I want you to think just about that. So here's the experiment that Lauren ran. She used subgoal labeling to teach Android App Inventor. There's 2 groups of undergraduate students. One gets those lists of steps and gets the video. Another group gets the video and steps with the subgoal labels inserted. And here's the outline for the experiment. First, students watch the video, either kind, and then take a test to demonstrate they understood it. Could they do the things that they just saw in the video? Go away for a week. Come back. Can you do the things that you saw a week ago? That's retention. Now I'm going to have you watch a new video about building a new app. We'll do a little bit to see whether or not you could do the things you saw in the second video. And then I'm going to give you a new problem. You have not seen a video for this. You've not seen a list of steps. I want you to build a new app. So that's about transfer of knowledge. Can you transfer the knowledge you learned from these other 2 apps into a new app that you haven't seen the code for before? Understanding, retention, and transfer, pretty small change. So here are the results. First, the students who get the subgoal labels attempt more steps and they get more correct, statistically significant difference. Okay, so it works in terms of learning. Subgoal labeling helps people to be able to learn the steps so they can do it themselves immediately afterward. Go away for a week, come back. Can you still do it? There's not a statistically significant difference in the number of steps attempted, but there is in terms of the number that they get correct. And Lauren has said that part of the reason why there's not a statistically significant difference in the number of attempted is that folks who didn't get the subgoal labels, they're kind of thrashing. They're kind of pulling out lots of blocks to try things out because they don't really remember. And it makes it hard to figure out whether they're attempting a step. Now, in the transfer task, one of the things that the students had to do was pull out a built-in UI element and associate a variable with it. The folks who got subgoal labeling could, those who didn't, couldn't. This is a really dramatic result. So these very small changes to the list of text instructions, to the list of videos, resulted in better understanding, better retention, and better transfer. Lauren has replicated this experiment with high school teachers. The effect is twice as strong. Why it's twice as strong, that's something we still don't understand. But it totally works for audiences that aren't just undergraduate students. In work with Brianna Morrison, Lauren and Brianna have shown that it works with text-based programming languages too. Subgoal labeling is this really powerful tool that improves the efficiency and the effectiveness of computing education. If we're serious about reaching CS for all, we have to think about making computing education better. And it turns out we now know a bunches of ways of doing this. Barbara Erickson has been studying Parsons Problems, invented by Dale Parsons, a teacher in New Zealand. Parsons Problems, I'm going to give you a programming problem, and I'm going to give you all the lines of code which correctly solve the problem, but they're on refrigerator magnets. Put them together in the right order. We can add distractors. It makes the problem more difficult. Barbara's been building adaptable Parsons Problems and has been finding that students who learn with Parsons Problems can write code on an exam just as well as students who learned by writing code. We know that worked examples are really powerful for learning in computer science and are often more efficient than having students solve another problem. We know that pair programming, having students work together at a keyboard, can lead to much better learning and can lead to a better social context, so the students are more likely to be retained in computer science. In my own work, I came up with a way of teaching computer science called media computation, where students are manipulating pixels of a picture, or as you saw, samples of a sound. And what we find is that the students have increased motivation to stick with computer science because it's relevant to them. They recognize the relevance of this manipulation of digital media. And so the argument is that if we want to reach everyone, we'll have to make learning computing more effective and efficient, because we can't expect people to slave through difficult programming languages for many, many hours before they're actually to do something that they find relevant and interesting. We're going to have to figure out ways of reducing cognitive load and teaching computer science in ways that can reach everybody. So let me get back to our timeline. 1961, Forsyth uses the term computer science in Journal of Engineering Education. Alan Perlis says this is for everybody. 2019, SIGC's 50th anniversary. So when will we achieve computational literacy for all? Let me give you a couple of stats to keep this in mind. Last year, the American Society for Engineering Education turned 125 years old. The National Council of Teachers of Mathematics was founded in 1920. Next year, they're going to be 100 years old. The American Association of Physics Teachers was founded in 1950. The Computer Science Teachers Association was founded in 2004. SIGC is only 50 years old. We've got a long way. We're really new at this. I kind of suspect that we're still going to be trying to figure out computational literacy for all, that we're going to be trying to realize Alan Perlis's vision when SIGC celebrates its 100th anniversary.